You will notice that we are spending a lot of our time in chapter 3 of Shigley's book, which I show a picture of here. And for today, we will be covering sections 3:14 roughly through 3:16. We'll see how far we can get. It is the stress inside the parts that is eventually going to cause failure of those parts, assuming it's being used the way it's supposed to be used. So it's important that we understand how the forces that are acting on components or structures are giving rise to stress states in those components or structures. So this section of the class, we start to talk about internally pressurized cylinders, and the best example of those internally pressurized cylinders are pressure vessels. This is an example of a pressure vessel right here. It's a classic pressure vessel that consists of a cylindrical portion and end caps. This one has supports, and it also has an access hole at the end. So we need to understand what are the stress states in the cylindrical portion of it, what are the stress states in the end caps, what are the stress states near any access holes that generate stress concentration factors, and what are the stresses in the transition from the cylinder to the end cap. We must design any system that carries an internal pressure to be able to safely carry that internal pressure. Here's another image. This is from Strathclyde University in the UK, where it's showing a number of things that you need to think about when you look at pressure vessels. There will be residual stresses that are associated with weldments in those pressure vessels. There are stress concentrations associated with all of the access holes. There's a phenomenon called shakedown, where repeated load-unload changes the local stress state. Of course, these things are always subject to the possibility of the formation of cracks, and those cracks can actually lead to fracture of the sample. This is a really bad thing if fracture happens. There can be yield limits reached in the pressure vessel, which causes a localized plastic deformation. And then, of course, there's something called creep, where we get a slow change in dimensions over time. That can lead to changes in wall thickness, which can lead to local changes in the internal stress, which could lead to failure. There's another interesting thing down here. This shows the vibration of a pipe, but those vibrations of the pipe can lead to fatigue failures. So all of these things have to be considered. There are lots of examples of internal external pressure out there that we use every single day. A good example is brake lines, where we show the solid brake line, which then has a fitting and connects to a flexible brake line here, so that tire, which is attached through this arm right here, can actually move up and down. And so we need a flexible pressure hose to be able to handle that. There are air conditioning lines both in our houses and in our vehicles that all are pressurized. So we have to be able to design all of those things to be able to handle the internal pressures. So we must know what the internal pressures are on the specific geometry we're exploring and how those are converted into stresses in the wall of the pressure vessel. Any through holes or any changes in geometry will give rise to stress concentration factors, and we have to understand how to calculate those and then how to design around them to prevent failure. If we do have a failure crack propagating in a pressure vessel, you want to make sure that the pressure vessel leaks before it breaks, because a leak decreases the internal pressure and reduces the possibility of catastrophic fracture failure. We have to look at all possible failure modes. I just want to use another example of some important pressure vessels that are out there. A boiling water reactor uses in the reactor, it is all contained within a pressure vessel. That is a pressure vessel, which is this pill-shaped device in here. And in a boiling water reactor, there is water over the fuel assemblies, but that water, as it passes by the fuel assemblies, it turns into steam. So this is steam up in here. The steam passes through a pipe, goes to a generator, a steam turbine, which spins, and then the steam must be condensed using a water condensation system and pumped back into the reactor as shown. This is a boiling water reactor. We have 35 of those in operation in the United States today, and it's important to note that this can be under some pretty significant pressure, and so this pressure vessel has to be able to withstand it. All the piping must be able to withstand it. The turbine must be able to withstand it. So you have to design all of these things to be able to handle the pressures they are expected to operate on. So let's just imagine stresses in a pressurized cylinder. So what we're going to do is just draw a cylinder here. I'm going to draw a thick-walled cylinder. Well, if the thickness is greater than 1/10 of the radius, then we have a thick-walled pressure vessel. And if we have a thick-walled pressure vessel, in this case subjected to both internal and external pressure, P sub I is the internal pressure, P sub O is the external pressure. The external pressure is, of course, pushing in on the outside of the cylindrical pressure vessel, and the internal is pushing out. So the internal pressure is trying to expand it, external pressure is trying to shrink it. If it is a thick-walled pressure vessel, as we move from the interior to the exterior of the pressure vessel, we find that there are two stresses that are of importance. If we take a little materials element out of it, we would note that that materials element would have radial stress, and it would also have a tangential stress. We know that the radial pressures are going to be compressive. They have to be. The tangential pressures, though, depend upon the internal and outside pressures that are acting on the pressure vessel. So the tangential stresses can be either tension or compression. And these equations here show how those pressures, both radial and tangential, this is the tangential pressure here, it's the radial pressure in the second equation. They depend both on the internal pressure, P sub I, the external pressure, P sub O, the internal radius, R sub I, and the outside radius, R sub O. And they vary with location R through the wall thickness. Now, if the outside pressure is 0, these equations reduce to a much simpler form. In fact, then the tangential pressure is given by this simple equation. R0 is given, that's the outer radius. Ri is given, that's the internal radius. And P sub I is the design pressure. And so we're trying to calculate what the tangential and the radial stresses through the wall thickness. So you're going to notice something here, and that is this factor out in front of both the radial and the tangential pressures is the same. The only thing that differs is the sign of R outer over R. The other thing you will notice if you look at it is that if the inner radius approaches the outer radius, then the pressure vessel goes from a thick to a thin pressure vessel, and these equations reduce to a much simpler form that the radial stress is small compared to the tangential. Well, that's the classic PR over T tangential pressure for a thin-walled pressure vessel. You've all seen that before. If ends are closed, so if you have a cylinder and you close the ends with some sort of end caps, then in addition to a tangential stress, sigma T, you end up with a longitudinal stress, sigma L, and the sigma L is just PR over 2T. So the tangential stress is always greater than the longitudinal stress. In fact, the tangential stress is twice the magnitude of the longitudinal stress, and we only have tangential and longitudinal stresses. The radial stress is so small compared to the tangential that we simply ignore it.